Welcome back. So, we have lecture 43 today and we will continue our discussion on bipolar devices. So, if you recall in the last lecture we just introduced BJT and we straight away moved to Gummel plot and to common emitter and common base, the physics of common emitter and common base. So, today we will start our discussion with Kirk effect and then we will go to Ebers-Moll model and so on. Okay. So, what the whiteboard here? So, Kirk effect is actually a high injection effect. So, what does it mean? It means that you have very high collector current, and for a very high collector current it means your emitter current is also very high. At very high collector current your gain will drop, your performance will degrade a lot. Okay. What do I mean by that? Let us go step by step. When you have a base collector region, suppose this entire region is your depletion region between the base and collector. Suppose this is your entire base and this is your entire collector, and this red shaded part is your base collector depletion region. What is there in the depletion region? You have positively charged ionized impurities in the depletion region, because the depletion towards the base is typically very small. The collector is more lightly doped. So, if I look at the base collector depletion, the depletion on the base side is very small, the depletion on the collector is very wide. So, most of the depletion happens towards the collector side, and the depletion is basically that there is all these positively charged ionized impurities, correct, because they have donated. This is there is a n-type doping in the collector. Now, when you have very high electrons flowing, very high current density, collector current density flowing, lot of electrons are basically swept across this depletion region, correct. Lot of electrons are swept across this depletion region. Remember the base collector depletion. So, electrons are swept away. So, lot of electrons are being swept away across the depletion region. So, in this depletion region, fast moving negatively charged electrons are coexisting with immobile positively charged ionized impurities. Electrons are mobile, ions are immobile, but they are coexisting in a temporal space. You can say fast moving electrons are basically traversing this terrain or this landscape of fixed immobile positive charges. Okay. If I happen to solve the Poisson equation at any instance of time, I want to do it, this will look like this: minus Jc by q v sat gives me the number of mobile electrons at any instant of time. Why? Because the current density is always charge times velocity. So, charge will be q times the mobile electron density per centimeter cube, of course, into velocity. The maximum current you can get is when the velocity is maximum, which is v sat, correct. So, J by q v sat will give you the maximum number of electrons that can go, alright, the maximum electrons that can go. So, this will give you the negative charge that is moving across this depletion region, and plus Nd of the collector, which is N collector here, is the background ionized impurity which is positively charged and which is immobile. The total of this is the total charge. So, the Poisson equation will say that the ratio of this total charge, the derivative of the total charge, it will say that the total charge by the epsilon is equal to the derivative of the field. I will say E is the field. This is the voltage basically. The voltage is basically charged by epsilon, and voltage is nothing but the field. Okay, the field. So, the derivative of the electric field is proportional to this. Fine. Okay, great. Now, so qualitatively, or if you can say semi quantitatively, if I keep increasing the base emitter voltage, I keep increasing the collector current, I keep exponentially, and I keep increasing the collector current, emitter current and hence collector current. I keep increasing the collector current as much as I want. What will happen? If the collector current is increased as much as I want, then this quantity will become larger and larger, which means there will be more mobile carriers. Okay. If given the saturation velocity has been reached, which means the electrons cannot travel any faster, a higher carrier density or higher current density means a higher carrier or mobile carrier concentration that is flowing across this depletion region. If this quantity becomes large, given this is fixed, this entire quantity becomes small because there is a negative sign in front of this, which means the slope of the field the slope of the field keeps reducing. This is the basic genesis of the Kirk effect. What people are plotting here is the output current, which is the collector current, plus the Gammel plot, and the base current with respect to the base emitter voltage, because that is the input voltage. You can see that eventually series resistance drops here, but eventually high injection drops here. Okay. Kirk effect is that your base will have, your base width will actually increase. We'll see how. Okay, it's a very interesting and bizarre effect. The base width will increase, and that's why the Kirk effect is also called the base width, push out, the base push out. The base has increased. If the base increases, then your current will fall, your cutoff frequency FT will fall, okay, and that's detrimental to your device. Okay. If your current, you need high current. Why do you need high current? Because a higher current will reduce the RC delay. There are so many capacitances in a bipolar device. We will see the real when we talk about the practical device layout. There are many parasitic actually capacitances in a bipolar device. Actually, the parasitics in a bipolar device are more than in a lateral HEMT or a FET device. Okay. So, you need to charge and discharge the capacitors as fast as you can, and for that you need a higher current density, because a higher current density leads to faster charging and discharging of the capacitors. That is why people want to go to as high a current density as possible, because the delay of the device reduces as the current density is increased. As the current density is increased, the GM also increases until Kirk effect happens at a certain current density, and we call that J Kirk. You want that the J Kirk should be as high as possible, which means you do not hit the onset of Kirk effect until a large current. That means your window of operation of the device till you hit the Kirk effect is large, and until you hit the Kirk effect, your transconductance will keep improving or increasing with increased collector current, and your delay will also reduce with increased collector current. This is very uncommon with respect to FET or MESFET, MOSFET, HEMT, etc., where the GM will not keep increasing indefinitely with an increase in the drain current. In fact, the GM will shoot and then fall. Your delay also will not reduce as you keep increasing the drain current. The drain current in an FET does not, with increase in drain current, your GM does not keep increasing, your delay does not keep reducing. It happens, however, in a bipolar device. That is why you want a higher current density to operate your RF devices until the Kirk effect sets in. So, now I will talk about different situation when your collector current is being increased, your slope of the electric field is decreased. So, how does it look like? Initially, it will look like something like that, this picture, where forget the base depletion and the base field is very narrow. There is a peak electric field here at the base collector depletion, as we all know, and the electric field looks like triangular, which we all know from basic semiconductor physics. This is your depletion. The depletion will keep expanding as you keep applying more and more, injecting more and more collector current. So, you see the depletion keeps expanding. The slope keeps reducing. This is the slope. The slope keeps reducing. At one point, the entire collector will be depleted. The entire collector will be depleted, and the slope has also become lower. Subcollector is little highly doped. That is why the subcollector will not be able to deplete as much. So, what will happen is that it will assume like a trapezium shape here. The slope is further reduced. You keep, and this is with increasing as I going from here to here, I am increasing the current density. From here to here, I am further increasing the current density. Here to here, I am further increasing the current density. Here to here, I am further increasing the current density. At one current density, the slope will become 0, which means there is a constant field. It's not a triangular field profile anymore. There is a constant electric field in the collector depletion. And beyond that, as I go from here, the slope will reverse, because minus J by Q V set plus N doping of collector, this quantity will become negative, because this has become very large, the collector current, and that is why the slope has become negative. The slope has become negative. Okay, the slope has become negative. Keep increasing more, this will become more negative, Eventually, the holes from the base the holes from the base will spill over to the collector, because this at this point the field will become 0. If the field becomes 0 like this, you see this point the field has become 0, and it's a negative slope, very steep negative slope. What does it physically mean? It physically means that at the base collector junction there is no field. If there is no field at this base collector junction, then all the holes that are here will face no barrier to spill over to the collector. So they will spill over to the collector, and the base width has increased by this quantity. So this is called a base push out. Base holes have spilled over to the collector because there is no field to prevent, and you know, in a depletion there is always a field that prevents the holes from coming from p side to n side and from electrons from migrating from n side to p side, but there is no field here, so you have stopped that. So the base, the holes can spill over to the collector side, and the base width has increased. Okay, with the increase in the base width, the gain will drop sharply, the cutoff frequency will drop sharply, delay increases, that means, and your overall device suffers now. Okay, because your gain cutoff frequencies they are dropping. To prevent this, you need the so essentially your threshold for Kirk effect, J Kirk, is your Q times the collector doping times the velocity saturation. You want this quantity to be as large as possible. That means the onset of Kirk effect should be large. Velocity of saturation, though we cannot change it because it's a material property. I mean, to some extent you can do it in a compound semiconductor, gallium arsenide, gallium phosphide family. You have so many alloys, you can choose which material has a higher velocity saturation, you can take that. But then typically materials with higher velocities tend to have lower breakdown voltages, so then that's does not help typical, because your lower breakdown voltage will also be very, very detrimental to your device performance. The only way to increase the Kirk effect is to increase the doping of the collector. If you increase the doping in the collector, again what will happen is that your breakdown voltage on the collector side will be low. So essentially, to get rid of Kirk effect to a large extent, you are sacrificing a breakdown voltage. That's the design optimization. BJT or bipolar devices are full of design optimizations. There is also design optimization for FET, but in bipolar devices they are very sharp. The early effect, for instance, the base emitter doping ratios, the Kirk effect versus the breakdown, the delay versus the the base resistance, because you have to thin the base down for a reduced base transit delay. A thin base also leads to higher base resistance, that is bad for noise, that's bad for Fmax. So these trade-offs are always there in bipolar devices, but that's how life is. Okay, so this is a Kirk effect. This is a serious effect for high power, high current RF devices. Okay, let's keep that in mind. Next we go to Ebers-Moll model. Okay, so this is a simple model. Well, when I say simple, it can be very complicated, by the way, but here we'll talk in a simple way. It's basically a model that is very useful for things like, you can have this model in a SPICE model, where you can do some device modeling, for instance. It's a simple physical or circuit based model, and you talk about the bipolar device as two coupled diodes. Actually, there's a base emitter diode, there's a base collector diode. You talk of them as coupled diode, and in all modes of operation, whether you are in active forward active mode or cutoff mode or whatever mode, you can model everything using a set of equations. Okay, so what happens is that this is your base emitter diode, this is a base emitter diode, this is a base collector diode. They are forward bias, reverse bias, they could be anything, of course. And then this current alpha R times IR, R stands for reverse, F stands for forward, but you can switch them back and forth, not an issue. Alpha R IR represents the current that will flow in the base emitter diode. Alpha R represents the alpha or the current transfer ratio when you refer from the output side to the input side, and alpha F is the current transfer ratio, okay, when you refer from the input side to the output side. So alpha R, alpha F. So this alpha R IR is the current that it's like a current source here, and the alpha F IF is the current source in this diode. Okay, of course eventually you are having the emitter current flowing in, the collector flowing in here, and the base is here. Okay, so what you can do is that the collector current, which is this, can be expressed as some exponential of the base emitter voltage plus some exponential of the reverse bias base collector voltage, right? And of course you have this alpha R IC and some minus IES. This is like the It depends on the q times d times ni square etc n by nd etc, right. Those constants are there actually. Okay. Similarly, the collector current here can be expressed as the forward current transfer ratio times some dependence on the forward bias and some dependence on the reverse bias. So there are different unknown parameters here, alpha r, alpha f for instance, I don't know exactly. So how do you find those out? And once you know those, then you can build the whole model. This model can be useful for something like spice modeling, as I told you, right. So we need to find out these unknown parameters, and there are ways to do that actually. So in this model we have not added any parasitic resistances, capacitances, but in general, to make it more accurate, you can include all kinds of parasitic resistances and capacitances. This expression IES and ICS, this is like the prefactor, you can say, on the exponential. This is the expression for that. You don't have to memorize anything, just this hyperbolic comes because the real derivation is actually hyperbolic. For a short diode it becomes linear, for a really long diode it becomes exponential. The hyperbolic function becomes exponential for a long diode, the hyperbolic function becomes linear for a short diode. That's how we get the linear and the exponential dependence, but otherwise actually it is truly hyperbolic. Okay. So these are the expression for that. These are like diode expressions, of course. So the way you find this out is, for instance, these different quantities alpha s, alpha f, alpha r. For instance, you can short the base collector diode. If you short the base collector diode, what will happen? This quantity is VCB is 0. E to the power 0 is 1. 1 minus 1 is 0. So this quantity goes. If you short the base and collector, then what happens is that your emitter current is purely based on this, no? Right? And your collector current is purely based on this. So if you short the base and collector, then this quantity becomes 0. Then your collector current can be expressed as a function of this. If you know IES, which is this, correct, then you can actually base emitter voltage, you can find out alpha f. Okay. Similarly for alpha r, you can short the base emitter, for instance. Okay, and you can keep the base collector at some reverse bias and you can get alpha r. So this is how you find out alpha r, alpha f. And in externally, if you look, it looks like a PN diode behavior, but actually there is a two coupled diodes. Okay, there's a two coupled diodes, and it can have more complications if you bring in parasitics. So here, as I said, alpha n minus IC by IE at VCV equals 0. If you short the base collector, then the ratio of the collector to the emitter current will give you alpha n. Similarly, short VBE, you get alpha r and so on and so forth. So this is how you actually build the model or you extract the parameters, but this is a very simplistic level. In a real simulator, it will be more elaborate. Please keep that in mind. The next we talk about is base transit time. What is the base transit time? It's a part of a total delay that the device will have. When the electron goes from emitter to collector, there's a certain delay it takes, certain time it takes. Base transit time is one of those components of delay. So base transit time basically means how much time the electron takes to travel across the base. And to a first order, this can be basically expressed as the total minority charge that is stored in the base. So this is a base, the neutral base, by the way. This triangle is a minority base profile, the injected electron minority in a p-type base profile. The area under the triangle is the total minority charge stored in the base at any instant of time. Okay, the total minority charge, the total, call it QF here, the total minority charge that is stored in the base, which is the area of this triangle, okay, divided by the current that is flushing out this charge. What is the current? The current is the collector current. You are injecting emitter current from here, some amount is lost in the base due to recombination, but most of it is going to the collector. So the collector current is basically taking the charge away. Think of this as like a reservoir of charge, and there is a current that is cleaning out the charge. Okay, so this collector current is like the flushing out of the charge. This current is flushing out the charge, and this is the charge that is stored in the base. So the minority carrier charge stored in the base divided by the current that is clearing the charge out. This ratio is the time taken for the electron to travel across the base, or you can say this is the base transit time, tau b. You can call it tau f, you can say here. Okay, this is the minority carrier charge divided by the current that is flushing it out. Okay, so that is your base transit time, and this is a very important component. And the base transit time, if you do the math here, it comes out to be the width of the base, this is the neutral base width by the way, times 2 times the diffusion coefficient of electrons in the base. This 2 could be slightly different depending on the design, you know, if you have a graded base for instance it could be different, but in general this is 2 times dn. So this is the base transit time. You can reduce the base transit time to improve the cutoff frequency by reducing the base thickness, because the diffusion coefficient is something you do not have much control on. Okay. And the diffusion capacitance associated with this, because the base emitter junction is forward biased. A forward biased junction has a diffusion capacitance, and this diffusion capacitance can be substantial. And because, you know, a base emitter junction being, it's a emitter base, because this is forward biased, this has this diffusion capacitance, and the diffusion capacitance can be significant. So that diffusion capacitance turns out to be transconductance times the base transit time. The diffusion capacitance can be significant, and the diffusion capacitance can actually lower the overall cutoff frequency of the bipolar device. Okay. Although on paper the bipolar device looks far more promising than FET compared to, as far as the cutoff frequencies are concerned, but the diffusion capacitance can be really killer. A diffusion capacitance can be really a killer because it can be really large. So the GM times tau f, the transconductance times the base transit time to a first order gives you the diffusion capacitance. How did they find out? They found out by the charge that is stored here, with the derivative of the charge with respect to the base emitter voltage, which is creating the charge with respect to the voltage. Okay. So the charge basically from this equation is the transit times the collector current, and is the base emitter voltage. If you take this tau f out of the equation, then DIC by DIVB is your GM. So that's why it's GMF tau f. Okay. So this is your diffusion capacitance here, and the area under the triangle, maybe I can remove the annotation here. The area under the triangle, okay, the area under the triangle is basically given by this expression where this is your half into height into base, the base is WB, so WB by 2, half of base into this is basically the minority carrier concentration at the edge of the base emitter depletion, and that's precisely n dash 0. Okay. This is an expression, if you plug in all these values differently, and on this expression you get tau f to be WN square 2 and 2 dn, which is precisely what I said. Now this is something very important that I am going to tell here, which is that this, in a base there are many current components. If the recombination is the primary component of the base current, which means the injected electrons are getting recombined in the base, and that is the major component of the base current, which means leakage, surface recombination, etc. are not the major component. The recombination is the main component. Then the recombination current of the base can be expressed as the charge stored in the base, the minority carrier charge stored, divided by the minority carrier lifetime in the base. The charge stored in the base divided by their lifetime, the minority lifetime in the base, that ratio is the recombination current. It makes sense, right? Because this is the minority carrier lifetime, which means this is the average time over which an electron hole will recombine. So the recombination current that arises because of the recombination is equal to the charge stored divided by recombination lifetime. So then the gain of the device beta, which is IC by IB, okay, from this expression IC is nothing but QF by tau f, and from this expression IB is nothing but QF by tau b. So this is tau b by tau f, which means the minority carrier lifetime divided by the base transit time is your beta, provided only the recombination is the dominant current component in the base. If your back injected holes from the base to the emitter is a dominant component, then this will not hold true. So lifetime, the minority carrier lifetime by the transit time in the base, the ratio gives you beta to first order. Just please remember that. Okay, just please remember that, it's very important. Now is there a chance to reduce this transit time? Yes. The way to reduce this transit time is basically to introduce a separate field in the base. You can make the electrons travel faster in a base by introducing an additional electric field in the base, and that additional electric field in the base can be done by doing something called grading, especially in something like if the base is, and we will talk about this, if the base is made of an alloy like say indium gallium arsenide in a 3,5 semiconductor, or it is made in silicon germanium in a BiCMOS technology, then you can compositionally grade the band gap of the material such that there is an additional electric field in the base even at equilibrium just because of grading. What it means is that your band gap might look something like that. Your band gap is continuously changing, there is a slope here. So the electrons that are here experiences a field already without the application of any bias. This is an additional electric field that is tailored, or that is generated or induced because of the grading of the composition of the alloy. This is called a quasi electric field. This is called a quasi electric field. So with that we will end today's lecture, where we discussed about the Kirk effect, the Ebers-Moll model very briefly, and then we talked about the base transit time. But we have to remember that for the total delay of the device, base transit time is just one part of the total delay, but it is a very important part. We will talk about the other parts later. Okay. So, and we talked about how to make the base transit time go reduce it even further by introducing a grading. We will talk about that also when you talk about silicon germanium HVDC in more details later. Next class we are going to talk about next concepts like a small signal model, extraction of cutoff frequency and so on. Okay. So, thank you for your time. I will see you in next lecture.